Hi, I am Mohammad Gorji, a master's student in artificial intelligence at the University of Tehran. Here is my final presentation for Bio-Inspired Computations course. So let's embark on an exciting journey into the transformative world of computational neuroscience, where foundation models are rapidly reshaping our understanding and analysis of neural data. This presentation, titled The Rise of Foundation Models in Computational Neuroscience, will provide a thorough exploration of the architectures behind these models, their diverse applications, and the future directions they have steering the field toward. At its core, this topic highlights how foundational models, large-scale pre-trained neural networks, are becoming pivotal tools in decoding complex brain signals. Unlike traditional models tailored for narrow tasks, foundation models are designed to be flexible and adaptable, offering a unified framework that can be applied across various problems in neuroscience. As we delve deeper, it's essential to appreciate the significance of this shift. Foundation models leverage massive dataset and advanced learning techniques to capture intricate patterns in neural activity, enabling breakthroughs in everything from brain-computer interfaces to understanding cognitive process. Their ability to generalize across different subjects and tasks marks a significant leap forward compared to earlier models. Building on this overview, the next part of our discussion will focus on the paradigm shift that have occurred in neural signal processing itself. We will trace the evolution from the early days of handcrafted feature engineering, where researchers manually designed task-specific features, to the adoption of classical machine learning, followed by task-oriented deep learning methods. Ultimately, we will see how foundation models emerge as a powerful solution that overcomes many of the limitations faced by previous approaches, offering scalability and adaptability that were once out of reach. Okay, let's explore the transformative journey of neural signal processing, tracing how the field has evolved from manual, handcrafted techniques to the cutting-edge foundation models we see today. This timeline highlights key paradigm shifts that have shaped how we analyze and interpret brain signals. Initially, neural signal analysis depended heavily on handcrafted feature engineering. Researchers manually designed features tailored to a specific task. Um, think of it as as crafting custom tools for each uh, unique problem. While effective in narrow context, this approach lacked scalability and adaptability, making it difficult to apply the same method across different dataset or experimental conditions. The next phase introduced statistical and classical machine learning methods, bringing more structure and rigor to neural data analysis. Techniques like principal component analysis, independent component analysis become staples for processing complex neural signals by reducing dimensionality and isolating sources. However, these methods still heavily relied on carefully engineering features and were often limited to a specific tasks, constraining their generalizability. Following that, the rise of task-specific deep learning models mark a significant improvement in performance and robustness. These models were designed and trained for particular neural tasks, allowing for better handling of complex patterns within the data. Despite these advances, they struggle with generalization across different subjects, or experimental setups, which limited their broader applicability. Uh, Most recently, foundation models have emerged as a game changer. By learning reusable and adaptable representations, these models overcome previous barriers by enabling scalability, robustness, and transferability across diverse neural tasks and populations. This shift opens new possibilities for more universal neural signal analysis frameworks that can adapt to varied contexts without extensive engineering. Um, Building on this foundation, the next phase introduced task-specific deep learning models like convolutional and recurrent neural networks. These models began to transform neural data analysis by enabling end-to-end and learning and automatic feature engineering, which we will explore in detail next. Let's explore how task-specific deep learning techniques, particularly convolutional neural networks, CNNs for short, and recurrent neural networks, RNNs, have shaped neural data analysis. These models have brought significant advances, but they also come with notable challenges that have limited their broader impact. First, the adaptation of CNNs and RNNs have allowed researchers to perform end-to-end learning directly from raw neural data. This means that instead of relying on handcrafted features, the models learn to identify relevant patterns automatically, streamlining uh, automating the analysis process. One of the key benefits here is hierarchical feature extraction, uh, which deep learning models can uncover multi-level features from simple to complex without manual intervention, which has a major bottleneck in traditional methods. Uh, was a major bottleneck. This capability has driven state-of-the-art performance in several important neural tasks, such as motor imagery, brain-computer interface, sleep staging, and seizure detection. These achievements showcase the power of deep architectures in capturing intricate neural dynamics. However, these successes come with limitations. The models tend to be narrowly specialized, excelling only in the specific task for which they were trained, which restricts their applicability across different problems. Moreover, they often struggle with cross-subject generalization. A model trained on one individual's data may not perform well on another's, highlighting the challenge of variability in neural signals. Another critical issue is the dependency on large labeled datasets. Acquiring and annotating these datasets is expensive and time consuming, creating a scalability bottleneck. As a result, manual labeling became a major hurdle in expanding these methods to a wider range of tasks. Finally, there has been a noticeable shift in focus from designing manual features to learning more breather representations. While this has improved robustness in some cases, it also points to the fragility of these models when faced with data variations outside their training distribution. So, building on this, the next phase in neural data analysis is revolutionized by the emergence of foundation models. These models address many of the limitations we have just discussed by leveraging massive unlabeled dataset uh, and self-supervised learning to develop versatile, transferable representations. So let's delve into how foundation models redefine our approach and open new opportunities in neuroscience AI. Let's explore a transformative shift in how we approach deep learning models, particularly in the context of neuroscience. This shift centers around what we call foundation models, a paradigm that fundamentally changes the way models are trained and applied across diverse tasks. At their core, foundation models are massive deep learning architectures pre-trained on vast, broad datasets without explicit labels, using a technique named self-supervised learning. This approach allows the models to learn general-purpose representations of data, capturing underlying patterns that can be adapted to a wide range of downstream tasks. Essentially, instead of building a model for one specific problem, foundation models provide a versatile starting point that can be fine-tuned efficiently for many applications. Key to this paradigm are several distinctive characteristics. First, these models undergo pre-training on general neural data, which equips them with a broad understanding, followed by fine-tuning tailored to specific tasks. Uh, this two-step process not only saves time and resources, but also leads to what we call emergence and a homogenization phenomenon, where the model develops capabilities that were not explicitly programmed and exhibits a consistent performance across different tasks. Uh, in neuroscience, an exciting development is the brain foundation models, which extend these concept to neural data like EEG, fMRI, and invasive EEG recordings. By capturing the complex spatiotemporal dynamics of brain signals, these models make it possible to reuse learned insights across various neurological applications, from diagnosis to brain-computer interfaces. The impact of this approach is significant. Foundation models help transcend the limitations of traditional task-specific deep learning, which often struggles with scalability and robustness. They enable more scalable, generalizable, and powerful computational tools that push the boundaries of what neuroscience AI can achieve. So, building on this foundation, we will next examine how neural signals analysis paradigm have evolved over time, and we will compare classical machine learning methods, task-specific deep learning, and foundational models side by side. Actually, we have done that, but we will focus more on the foundational model side. So, um, in the next slide, we would examine a table comparing these methods. So, let's explore how neural signals analysis has evolved over time through these distinct paradigms, each representing a significant shift in methodology and capability. This table summarizes the progression from classical machine learning approaches to the cutting-edge foundation models that are transforming the field. Here in this table, you can see a brief explanation of what we have already told in the previous slides. Uh, Now, let's explore the fundamental concepts behind self-supervised learning, which is rapidly becoming the driving force behind scalable foundation modeling, especially in neuroscience. At its core, self-supervised learning, or SSL, revolves around the idea of learning from unlabeled data, which is a game changer given the scarcity and cost of manual annotations. First, SSL allows models to learn useful representations by solving pretext tasks without requiring any manual labels. This means the model creates its own learning objectives from the data itself, effectively generating supervisionary signals automatically. For example, a model might predict missing parts of the input or identify relationships within the data, all without human intervention. The learning process typically unfolds in two stages: pre-training and fine-tuning. During pre-training, the model tackles these self-generated tasks on a large amount of unlabeled data, building a solid foundation. Then it is fine-tuned on a smaller labeled dataset for a specific downstream task, which significantly reduces the annotation burden. One of the biggest advantages here is the ability to leverage massive datasets of neural signals that are otherwise difficult to label. This unlocks tremendous potential for brain foundation models, or BFMs, enabling them to learn complex representations that capture the rich dynamics of neural activity. Importantly, this approach is highly relevant for neuroscience because it promotes a scalable and data-efficient modeling strategies. Instead of being limited by expensive data curation, researchers can harness vast amounts of raw neural data to build models that generalize well across different brain states and subjects. Uh, so, building on these foundational principles, we will next delve into the specific self-supervised learning techniques used to train brain foundation models. This includes methods like masked signal prediction, autoregressive modeling, autoencoders, and contrastive approaches, each with their own strengths and trade-offs, setting the stage for understanding how these techniques uniquely address the challenges of neural data. Let's delve into some of the core self-supervised learning techniques that have been pivotal in training brain foundation models. These methods enable models to learn meaningful neural representations without relying on extensive labeled data, which is often scarce or costly to obtain in neuroscience. At the heart of these approaches, we have reconstructive and predictive methods. Mass signal prediction, for example, works by intentionally obscuring segments of neural data and then training the model to predict those missing parts. This forces the model to develop a deep understanding of the underlying neural patterns, leading to robust feature representations. Techniques like BrainLM and EEGPT leverage this strategy effectively. Autoregressive modeling, on the other hand, uh, focuses on sequential prediction by forecasting future uh, neural signals based on past information. Models such as NeuroLM capture essential temporal dependencies, which is critical given the dynamic nature of brain activity. This sequential approach mirrors how we might naturally anticipate upcoming neural events. Autoencoders provide another powerful tool using encoder-decoder architectures to compress neural signals into a latent space and then reconstruct them. This process helps the model learn compact informative features that can generalize well across tasks. Uh, cont- uh, Contrastive methods take a different route by maximizing the similarity between different augmented versions of the same neural data while minimizing similarity across different samples. This encouraged the model to focus on discriminative features that define neural states or conditions. Key to these domain-specific augmentations for neural signals, these include techniques like time frequency consistency checks, psychologically based re, referencing to standardized signals, and cross-view contrastive learning, which compares different perspectives of the same neural event. Each approach has its trade-offs. Reconstructive methods tend to excel at capturing holistic patterns in the data, making them well suited for broad representation learning. Contrastive methods, meanwhile, shine at extracting features that are highly discriminative, which can be crucial for tasks like classification or anomaly detection. Uh, so let's explore the core architectural design that powers modern brain foundation models, especially how the transformer architecture plays a pivotal role in neural decoding. This slide highlights why transformers have become the backbone for interpreting complex brain signals and advancing computational neuroscience. At the heart of this approach is the transformer's ability to overcome the intrinsic limitations of recurrent neural networks. Traditional RNNs process sequences step by step, which creates bottlenecks and inefficiencies. And by using multi-head self-attention, transformers enable parallel processing of neural signals, dramatically improving both speed and performance. This is vital when dealing with the vast and complex datasets typical in brain research. Another key strength is the transformer's capacity to capture long-range temporal and spatial dependencies. Brain signals are not just isolated events, they involve intricate interactions across different brain regions and extended time intervals. The architecture's design allow it to effectively model these connections, preserving rich dynamics inherent in neural recordings. Maintaining the order of sequences is also critical. Transformers achieve this through positional encodings, which injects information about the position of each data point in the sequence. This ensures that the temporal structure of neural signals is accurately represented, a necessity for reliable decoding. Scalability is another important advantage. As brain datasets continue to grow in size and complexity, the transformers architecture can efficiently scale to handle this influx, making it practical to train the large-scale foundation models without compromising speed or accuracy. Moreover, transformers offer remarkable flexibility in modeling diverse and complex brain dynamics. Whether the neural patterns are straightforward or highly intricate, this architecture can adapt, making it an ideal framework for a wide range of neural decoding applications. Ultimately, these capabilities have positioned the transformers as the foundational architecture for most large-scale brain foundation models today, driving new insights and breakthroughs in understanding neural activity. Building on this architectural foundation, we will next examine how transformer-based models are especially tailored for EEG decoding. We look at different categories of these models, uh, backbone, hybrid, and customized variants, highlighting their unique strengths and challenges in capturing EEG data, spatial and temporal nuances. This comparative analysis will deepen our understanding of how transformers are adapted to meet the demands of real-world neural signal processing. Let's explore the landscape of transformer-based architectures applied to EEG decoding, focusing on how different model designs address the unique challenges of EEG data. This slide breaks down three main categories: backbone models, hybrid models, and customized variants, each bringing a distinct approach to capturing brain signals. Starting with backbone models, these are essentially vanilla transformer encoders, such as EEG transformer. Their strength lies in capturing global dependencies within EEG data, which is crucial because brain signals often involve long-range temporal and spatial interactions. However, they lack EEG-specific inductive biases, meaning they don't inherently account for the unique spatial or temporal structures characteristics of EEG recordings, potentially limiting their performance. Hybrid models combine the best of multiple worlds. For instance, CNN transformer models like ERTNet integrate convolutional layers that excel at locate feature extraction with transformers that model global attention. Similarly, GNN transformer architectures like SDGGT represent the spatial topology of electrodes as graphs, capturing relationships between electrode positions more naturally. Generative hybrids incorporate diffusion models or GANs alongside transformers to augment data or synthesize realistic EEG signals. These designs offer richer modeling capabilities but come with increased architectural complexity, requiring more careful integration of components. Finally, customized variants such as multi-component transformers uh, and hierarchical or pyramid architectures introduce specialized blocks tailored to regional brain features and multi-scale temporal dynamics. This approach enhances the model's ability to capture fine-grained details while maintaining efficiency. Nevertheless, these architectures demand meticulous design and tuning to balance complexity with performance. Understanding these different design is essential as they set the stage for how foundation models can be optimized for each data. But models alone aren't enough. Training such advanced architectures. Uh, these advanced architectures requires vast and diverse datasets. This naturally led us into the next focus, the large-scale neural datasets that are powering a foundation model pre-training in neuroscience. We will examine key datasets like the TUH-EEG corpus and the UK Biobank and discuss the challenges around data. Building on our exploration of foundation models in neuroscience, let's delve into the critical role that large-scale neural datasets play in powering these models. The scale and diversity of data are what enable foundation models to learn robust, generalizable representation of brain functions. First, pre-training these models requires vastly larger datasets than traditional task-specific deep learning. This is because foundation models must capture a wide range of neural patterns and variability to perform well across many applications, not just a single task. The sheer volume of data uh, help prevent overfitting and improves the model's ability to generalize to new unseen data. Uh, However, integrating such massive and varied data sets comes with significant challenges. Data heterogeneity, meaning differences in collection methods, population, and modalities, can complicate model training. Privacy concerns are paramount when dealing with sensitive clinical information requiring careful data governance. Additionally, the absence of standards uh, formats and protocols make harmonizing datasets a complex task. Yet overcoming these barriers is essential for effective model development. Um, Collaborative curation and sharing of extensive neural datasets from the backbone of progress in the field. Large consortia and open initiatives enable researchers to pool resources and expertise, accelerating advances in foundation models for neuroscience. For example, the Temple University Hospital, TUH, uh, has a massive dataset EEG corpus, which provides over uh, 60,000 clinical EEG sessions, enriched with physicians' reports that add valuable contextual information. Its subset, the TUHEG seizure corpus, for short TUSZ, contains approximately 500 hours of expertly annotated seizure data, enhancing model accuracy for seizure detection tasks. Uh, on the functional imaging side, datasets like UK Biobank and the Human Connect, Connectome project offer massive collections of fMRI data. These datasets are crucial for modeling brain activity and functional dynamics on a large scale. Additional EEG resources, such as the NMT Scope EEG dataset and the Healthy Brain Network juvenile data, introduce further diversity by covering different populations and developmental stages. This heterogeneity strengthens the foundation model's robustness and applicability across various neuroscience domains. In summary, the combination of data scale and diversity is what empowers foundation models to achieve high performance and reliability. The ability to generalize across different subjects, conditions, and modalities hinges on these comprehensive datasets. Next, we will review a detailed summary table outlining the key large-scale neural datasets fueling foundation uh, model pre-training. This table will highlight their modalities, subject counts, data volumes, and unique characteristics, and primary use cases, providing more clear picture of the resources driving innovation in this space. Uh, so in this table, you can see the properties of these datasets, and building on our exploration of AI applications in neurological diagnostics, let's delve into how foundation models are revolutionizing seizure detection. This approach leverages advanced unsupervised learning and deep modeling techniques to enhance both the accuracy and efficiency of epilepsy diagnosis. First, it's important to recognize that traditional epilepsy diagnosis heavily relies on manual EEG review, which is a tedious and a time-consuming process. Clinicians must meticulously examine lengthy EEG recordings to identify seizure events, which can slow down patient care and limit scalability in busy clinical environments. While conventional machine learning methods have achieved around 89% accuracy in seizure detection, more specialized deep learning techniques can exceed 95%, demonstrating the potential of AI to significantly improve diagnostic precision. However, these models typically require large label datasets, which are challenging to obtain given the rarity and variability of seizure events. This is where big foundation models, BFMs, come into play. BFMs are capable of unsupervised anomaly detection by learning typical brain activity patterns without needing labeled seizure data. By understanding what normal EEG activity looks like, this model can flag deviations that may correspond to seizure, for example, making detection more robust and less dependent on extensive annotations. The EEG CGS method further enhances this by integrating contrastive and generative learning on EEG graphs. This combination allows the model to better capture the complex and diverse nature of seizure abnormalities, improving sensitivity across different seizure types. Similarly, EpilepsyNet adopts a self-supervised framework that enables seizure detection without requiring explicit examples during training. This is particularly valuable for wearable devices where collecting labeled seizure data is impractical, thus facilitating continuous and user-friendly monitoring. Overall, foundation models address critical challenges such as data scarcity and the difficulty of labeling seizure events, paving the way for more reliable and automated detection tools in clinical practice. This advancement holds a promise not only for improving patient outcomes, but also for reducing the workload on healthcare professionals. Next, we will explore how similar foundation model techniques are transforming sleep staging. By boosting accuracy, reducing the need for extensive labeled data, and enabling early prediction of health risks, these models are opening new frontiers in sleep medicine and prognostic assessments. Let's explore how advanced prognostic models are transforming sleep staging, a critical step in understanding sleep health. Traditional methods rely heavily on manual scoring, which is not only time consuming, but also subjective, leading to variability between experts and limiting how widely these techniques can be applied in clinical settings. Machine, lear- uh, Machine learning has made strides here, pushing accuracy to around 80%, and deep learning has further improved this to about 90%. However, deep learning typically requires large amounts of the labeled data, which can be a bottleneck. This is where biomarker foundation models or BFMs like SleepFM come into play. We will talk about SleepFM in further slides. This is our main paper to discuss. Uh, so these models achieve comparable or even better accuracy while needing far fewer labeled examples, making automated sleep staging more scalable and efficient. Uh, Beyond just staging sleep, BFMs generate prognostic embeddings that can predict future health risks, such as neurological disorders and even mortality. This capability opens door to early interventions based on sleep data, shifting the focus from simply replicating existing staging methods to innovating personalized medicine approaches. Moreover, BFMs help uncover novel biomarkers that link sleep patterns with long-term health outcomes, providing deeper insights that can inform both research and clinical practice. This presents a significant leap forward in clinical neuroscience, moving the field toward more predictive and personalized strategies. Building on this theme of leveraging advanced AI models, we will next look at how foundation models are being applied to motor imagery brain computer interfaces, addressing challenges like calibration time and user variability to enhance device control through imagined movements. Let's delve into how foundation models can address some of the persistent challenges faced by motor imagery brain computer interfaces, or MIBCIs. These systems allow users to control devices simply by imaging movements, which is a powerful non invasive way to operate assistive technologies and neuroprosthetics. However, despite their promise, MIBCIs encounter several hurdles that limit their effectiveness and broader adaptation. Uh, One major challenge is the inherently low signal-to-noise ratio in motor imagery data. Uh, the neural signals generated during imagined movements are weak and often buried in background brain activity or environmental noise. Additionally, these signals vary significantly not only between difficult users but also within the same user over time. This variability complicates the task of accurately decoding the user's intentions. Another critical issue is what's known as BCI illiteracy, where roughly 20 to 40% of users struggle to achieve reliable control. This can stem from individual neural or cognitive differences, meaning that a sizable group simply cannot benefit fully from traditional MIBCIs. To add to these challenges, current systems require lengthy calibration periods for each user. This involves extended training sessions to tailor the system specifically to an individual neural patterns, which can be time consuming and inconvenient, hindering real world usability. Traditional approaches rely heavily on handcrafted features, manually designed signal characteristics, and personalized model training. While effective in some cases, this method limits scalability and adaptability, making it difficult to deploy MIBCIs widely. This is where foundation models come into play. These are AI models pre-trained on large diverse motor imagery datasets, enabling them to learn generalized neural representations that are robust across different users. By leveraging such models, we can drastically reduce or even eliminate the need for extensive calibration, thanks to their ability for few-shot or zero-shot adaptation. This means the system can quickly tune to a new user's signal with minimal or no additional training. Uh, the impact of this approach is significant. It not only improves the performance and reliability of MIBCIs, but also greatly enhances accessibility, enabling a broader range of users to benefit from these technologies without the frustration and long setup times or inconsistent control. Building on this understanding of foundation models in MIBCIs, we will now explore their practical applications and the exciting research advancements they are enabling. From brain decoding and clinical diagnostics to creating digital twins of the brain, These models are opening new frontiers in neuroscience and neurotechnology. Uh, let's delve into the diverse and impactful applications of brain foundation models, or BFMs, which are transforming both research and practical use in neuroscience and neurotechnology. At their core, BFMs enable us to interpret complex neural data and simulate brain processes in ways that were previously unimaginable. Starting with brain decoding, these models help us translate neural signals into meaningful information about mental states. This not only advances our understanding of cognitive, but also plays a crucial role in clinical diagnostics and assistive technologies, such as imagery brain computer interfaces, which we discussed earlier, or control devices through thought alone. In clinical diagnostics, BFMs are being used to detect seizures, accurately stage sleep phases, and predict neurological diseases by analyzing pattern in neural activity. This enhances early intervention and personalized treatment strategies. Assistive neurotechnology leverages motor imagery BCIs to provide alternative communication channels for those with motor impairments, uh, significantly improving quality of life, perhaps. Brain discovery is another exciting frontier. This is a very exciting topic where BFMs simulate brain activity to explore underlying biological mechanisms and neural computation principles. This virtual experimentation accelerates scientific insights without any invasive procedure. And also, digital twins of the brain represent a groundbreaking approach. Um, creating detailed computational replicas of individual brains. These digital models allow researchers to predict brain responses and disease progression, opening doors to personalized medicine. Finally, investigating neural coding through simulations helps decode how the brain processes and encodes information, deepening our understanding of neural computation and potentially inspiring new AI architectures. Building on this foundation, we will next explore how these modeling techniques are revolutionized sleep science. Especially, we will look at SleepFM, the main paper of our presentation. Uh, SleepFM, which harnesses multimodal polysomnography data to automate and enhance sleep analysis, uncover hidden health biomarkers, and shift the paradigm from diagnosis toward prediction and proactive care in sleep health. Building on the foundation of sleep science, this section highlights how SleepFM foundation models are set to revolutionize our understanding and analysis of sleep health. By leveraging multimodal polysomnography or PSG data, these models provide a comprehensive and automated approach to interpreting complex sleep patterns. First, the use of EEG, ECG, EOG, and respiratory signals allows us to capture a full spectrum of psychological activity during sleep. This multimodal approach goes beyond single signal analysis, giving us a richer and more detailed picture of sleep architecture and underlying bodily processes. Next, automating the sleep staging process is a game changer. Traditionally, sleep stages have been scored manually by experts, a process that can be time intensive and subject to variability. By using foundation models, we can scale this analysis efficiently and consistently, ensuring high-quality data interpretation without the bottleneck of human scoring. Another exciting aspect is the discovery of latent health biomarkers hidden within sleep data. These biomarkers extend beyond the conventional diagnostics, offering new insights into how sleep patterns may signal the onset or progression of various health conditions, potentially before clinical symptoms appear. Finally, this approach shifts the paradigm from simply diagnosing sleep disorders to predicting health outcomes. By moving toward prognostic medicine, we can anticipate risk and intervene earlier, ultimately improving patient care through a more proactive stance. Looking ahead, we will explore how AI-driven automation accelerates sleep analysis even further by addressing the challenges of manual scoring, enhancing predictive capabilities, and refining the accuracy of sleep staging and disease classification. This next step is critical in transforming raw sleep data into actionable holistic health insights. Excuse me, I'm getting tired a little bit, but let's continue and explore how AI automation is revolutionizing sleep analysis by addressing the long-standing challenges of manual scoring and prediction. This shift not only accelerates the process but also enhances precision in diagnosing sleep disorders and forecasting health outcomes. First, manual sleep scoring has traditionally been a bottleneck. It's time consuming and heavily dependent on trained experts, which limits scalability. By automating this process, we can analyze sleep data much faster and with consistent accuracy, freeing up valuable clinical resources. Next, we move beyond conventional sleep studies that often focus only on immediate symptoms. Advanced modeling now unlocks the prognostic potential of sleep psychology, allowing us to predict future diseases and even mortality risks based on subtle patterns in the sleep data. This represents a significant leap in preventive healthcare. To achieve this, we are developing a multimodal foundation model that integrates different types of psychological data. By combining signals like EEG, ECG, and respiratory patterns, the system can stage sleep and classify disorders with greater reliability than single modality approaches. Finally, instead of relying solely on traditional sleep metrics, we are transforming these diverse sleep signals into holistic biomarkers. These biomarkers provide a comprehensive view of systematic health, potentially revealing insights into conditions far beyond sleep disorders alone. Building on this foundation, the next step is to maximize the accuracy of SleepFM by leveraging an extensive and diverse dataset. We will delve into how training on over 500,000 hours of polysomnography data from tens of thousands of participants allows us to create a robust self-supervised learning model that captures the full complexity of sleep psychology across populations. Building on our foundation of advanced sleep analysis, let's explore how maximizing the accuracy of sleep FM relies heavily on an extensive and diverse dataset. This slide highlights the incredible scale and richness of the data underpinning our model, which is key to its robust performance. First, the model is pre-trained on over uh, 500,000 hours of polysomnography or PSG data gathered from about 65,000 participants, spanning multiple cohorts. Uh, this breadth ensures that the model learns from a wide variety of sleep patterns and demographics, enhancing its ability to generalize across different populations. It's not just about quantity, but also the diversity of the data that strengthens the model's insights. Next, we incorporated multimodal psychological signals to capture a comprehensive picture of sleep. EEG provides detailed information or on cortical brain activity. ECG tracks cardiac dynamics reflecting heart rate variability. EOG focuses on eye movements indicating of REM sleep stages, short for rapid eye movement, and respiratory signal monitor breathing patterns. Combining these modalities allows for a full spectrum understanding of sleep psychology, which isolated signals alone might miss. A major challenge in working with such complex multimodal data is pre-processing. Here, rigorous standardization was applied, aligning sampling rates and electrode montage, removing artifacts, and synchronizing segments across all signal types. This cleaning process ensures that the data fed into the model is both accurate and consistent, which is crucial for reliable learning outcomes. Finally, all this effort can all this effort culminated in the creation of a coherent large-scale dataset tailored for self-supervised learning. By enabling the model to learn from the data itself without heavily reliance on manual labels, we enhance both its accuracy and generalizability in sleep analysis tasks. Looking ahead, we will delve into how this rich multimodal data is leveraged through a sophisticated convolutional neural network architecture. Especially, we will examine the use of modality-specific CNN encoders and an innovative leave-one-out contrastive learning approach that aligns embeddings for a unified representation of sleep psychology, physiology. This next step is vital for unlocking deeper insights from the complex signals we have just discussed. Building on our exploration of sleep data, let's now delve into how we unlock deeper insights by integrating multiple psychological signals through an advanced neural network architecture. This approach harnesses the power of EEG, ECG, EOG, and respiratory data to create a comprehensive picture of sleep physiology. Uh, at the core, we use modality-specific convolutional neural network encoders to extract rich and distinctive features from each type of signal. For example, EEG data reveals intricate spectrotemporal oscillations that are fundamental to understanding brain activity during different sleep stages. ECG provides valuable information about heartbeat variability, which can reflect autonomic nervous system dynamics. Eye movements captured by EOG help identify transitions between sleep stages, especially REM sleep, while respiratory signals offer insights into breathing rhythms, critical for detecting disorders like apnea. To effectively combine these diverse signals, we apply the authors of the paper, applied a leave one out contrastive learning strategy. This means the model systematically withholds one modality at a time during training. Encourage it to learn shared psychological patterns rather than overfitting to modality, specific artifacts or noise. This approach ensures the embedding from each modality align closely in the feature space, promoting a unified understanding of sleep physiology. The result is a robust multimodal foundation representation that integrates these varied physiological inputs into a single consolidated vector. This unified representation improves both the accuracy and reliability of downstream sleep analysis tasks, as it captures complementary information that no single modality could provide alone. Moving forward, we will see how this powerful multimodal approach translates into real-world performance, especially and looking at SleepFM's impressive accuracy in sleep staging and apnea detection. This next section highlights clinical grade results that demonstrate the practical impact of integrating these sophisticated uh, sleep insights. Building on our understanding of advanced sleep analysis, let's dive into how SleepFM achieves exceptional accuracy in both sleep staging and apnea detection. This slide highlights the model's impressive performance metrics and its clinical relevance. First, SleepFM excels in robust five-class sleep staging, accurately identifying wake N1, N2, N3, and REM stages with mean F1 scores ranging from 70 to 78%. To put this in perspective, these scores are on par with or even exceed those of specialized deep learning models tailored especially for stage classification. This level of precision is critical, but accurate staging forms the foundation for reliable sleep assessments and downstream clinical applications. Uh, Next, SleepFM leverages label-efficient self-supervised learning. This means the model can pre-train itself on vast amounts of unlabeled sleep data, substantially reducing the need for labor-intensive manual labeled datasets. This approach not only accelerates development but also maintains high accuracy in sleep stage classification, making the technology scalable and adaptable to new settings or populations. When it comes to detecting sleep apnea, SleepFM achieves IURC curve values between 90% and 94%. These scores reflect clinical grade accuracy, comparable to expert human scoring systems used in sleep clinics. This capability is particularly significant because sleep apnea is a uh, uh, prevalent but often underdiagnosed condition linked to serious health risks. Reliable automated detection supports timely diagnosis and intervention. Finally, the model shows a strong generalization across different datasets, meaning it performs consistently regardless of variations in in the input data. Importantly, SleepFM also offers interpretable outputs, which increases clinical trust and facilitates integration into both research and clinical workflows. Interpretability ensures that end users can understand and validate the model's decisions, a crucial factor in healthcare settings. Moving forward, we will explore how SleepFM's predictive embeddings extend beyond sleep analysis to forecast the risks for over 130 diseases, including dementia and heart failure. This transformative capability leverages the rich information embedded in sleep data to provide early warnings for clinical health conditions, opening new avenues for preventive medicine and personalized care. Let's explore how SleepFM's predictive embeddings are revolutionizing the way we understand and utilize sleep data for disease prognosis. This slide highlights the remarkable capability of SleepFM to predict the risk of over 130 diseases, including critical conditions like dementia and heart failure. By transforming complex sleep patterns into actionable early warnings. First, the system's ability to predict risk across more than 130 diseases represents a significant leap beyond traditional sleep analysis, which typically focuses on sleep quality or disorders alone. By embedding sleep data into predictive models, the SleepFM offers clinicians a comprehensive tool to anticipate a wide spectrum of future health issues, paving the way for proactive and preventive care. Looking at specific examples, the dementia prediction achieves a C index of 85%. This metric indicates a strong prognostic accuracy, meaning SleepFM can reliably identify individuals at high risks for dementia well before clinical symptoms manifest. Early detection is crucial here, as it opens opportunities for interventions that could slow progression or improve quality of life. Similarly, the model predicts heart failure risk with a C index of 80%. This level of accuracy supports a timely clinical decision making, helping healthcare providers allocate resources efficiently and potentially prevent acute episodes through early management. Lastly, SleepFM also forecasts all-cause mortality with a C-index of 84%. That's very interesting. This robust mortality risk assessment can inform personalized health strategies, enabling targeted interventions tailored to an individual's overall health trajectory. Together, these data points illustrative how SleepFM's embeddings bring unprecedented depth and precision to prognostic medicine. Using sleep data as a window into broader health outcomes. Building on this predictive power, the next focus will be on how SleepFM maintains its effectiveness across different populations and clinical scenarios. We will see how its robust transferability and few-shot learning capabilities make it highly adaptable, scalable, and practical for deployment in diverse healthcare settings. Building on the foundations we have discussed earlier, let's explore how SleepFM unlocks robust transferability in clinical AI models, making them both scalable and adaptable across diverse populations and tasks. At its core, SleepFM is designed to generalize well beyond the datasets it was initially trained on, which is crucial in clinical settings where patient cohorts and conditions vary widely. First, SleepFM ensures strong generalization across different cohorts, meaning it maintains high performance even when applied to new population groups or clinical tasks that differ from its original training data. The adaptability is essential for broad clinical applicability as it reduces the risk of model failure when faced with unexpected variations. Next, the model leverage powerful transfer learning capabilities. Rather than starting from scratch for each new dataset, SleepFM efficiently transfers what it has learned, drastically cutting down the time and resources needed for retraining. This is particularly valuable in healthcare, where label data can be scarce or costly to obtain. Another key feature is the ability to fine-tune the minimal labeled data. SleepFM requires only a handful of labeled examples from a small external datasets to customize its performance effectively. This few-shot learning approach enables rapid adaptation to new environments without extensive data collection efforts. Scalability is also at the forefront. SleepFM supports deployment across multiple institutions and clinical environments, which facilitates wider adaptation and help standardize AI-driven diagnostics and treatments. Scalability promotes consistently in care while accommodating institutional differences. Additionally, the model promotes reproducibility and adaptability. uh, it delivers a consistent result across various settings and can be easily adjusted as clinical needs evolve, fostering trust and reliability in real-world applications. Finally, SleepFM enhances practical utility by extending its usefulness beyond the original data and task it was designed, uh, trained. This flexibility maximizes clinical relevance, allowing healthcare professionals to apply it to emerging challenges and diverse operational scenarios. With this strengths in transferability and scalability, we set the stage to address the clinical challenges in brain model development. Up next, we will delve into how we can overcome issues like data diversity, computational constraint, interpretability, and bias, all essential for advancing brain AI models that are both effective and fair. As we delve deeper into the complexities of brain model development, it's crucial to acknowledge the significant hurdles we faced on this journey. This slide focuses on four key challenges that must be addressed to advance brain AI models efficiently and responsibly. First, data heterogeneity and scarcity present a major obstacle. Brain data comes from diverse sources with varying collection protocols, which make aggregation difficult. Moreover, rare conditions and minority groups often have limited labeled data, hindering model performance and generalizability. To tackle this, federated learning offers a promising solution by enabling data sharing across institutions without compromising privacy, allowing models to learn from a broader and more diverse datasets. Next, managing computational cost and scalability is vital. Training advanced models demand enormous resources, which risk centralizing development to only well-funded entities. Research into more efficient architectures like Mamba, combined with parameter-efficient fine-tuning techniques such as e.g. graph adapter, help reduce this burden. These innovations allow us to scale brain models without prohibitive cost or infrastructure. Enhancing interpretability and trust is another cornerstone. Brain AI often acts as black boxes, making clinicians uh, hesitate to rely on their outputs. By using post hoc explanation methods and designing intrinsically interpretable models like EEG GPT, we can provide clearer insights into how these systems reach their conclusions, fostering greater clinical adoption and confidence. Finally, detecting and mitigating bias is essential for fairness. The training data can embed demographic biases that, if unchecked, lead to unfair or inaccurate predictions. Systematic testing approaches like mm, tri-pro testing help identify these biases, while mitigation strategies such as adaptive logic adjustment work to correct them, ensuring more equitable outcomes across diverse populations. Building upon these technical and ethical challenges in development, we now turn our attention to the broader ethical landscape. Next, we will explore how to protect privacy, prevent misuse, and navigate regulatory challenges in neuro AI. Ensuring these powerful technologies benefit society while respecting individual rights. As we delve deeper into the intersection of neuroscience and artificial intelligence, it becomes crucial to address the ethical landscape shaping neuro AI development. This segment focuses on protecting fundamental ethical standards to ensure that advancements benefit society without compromising individual rights or safety. First, safeguarding mental privacy and cognitive liberty is paramount. While emerging mind reading technologies, there is a risk of invasive access to our thoughts and cognitive processes. It's important to foster broad discussions about cognitive rights, essentially, the right to keep one's mental life private, and establish clear ethical boundaries to prevent misuse. Next, neural data security and informed consent must be treated with the utmost seriousness. Neural data is highly sensitive, akin to personal health information. This calls for rigorous anonymization techniques and robust security protocols to protect this data. Moreover, as AI models evolve, individuals must be fully informed about how their neural data will be used, ensuring consent remains transparent and ongoing. We also need to anticipate dual use risk inherent in neuro AI technologies. While these tools hold incredible promise for medical breakthroughs, they could also be weaponized or used in a discriminatory ways. Uh, Scientists and developers carry a responsibility to proactively identify and mitigate such risks before they manifest. Finally, addressing regulatory challenges requires interdisciplinary collaboration. The rapid pace of neuro AI innovations has outstripped current legal and ethical frameworks. Bridging these gaps demands a partnership across neuroscience, law, ethics, and policy to create comprehensive governance structures, what some call neuro-rights, that keep pace with technological advances. Building on this foundation, ethical vigilance, we now turn to how brain foundation models are harnessed to drive transformative applications in neuro AI. These scalable brain signal models are revolutionizing neuroscience by enabling state-of-the-art clinical tools and unlocking new prognostic capabilities, all while emphasizing the importance of ethical, uh, interdisciplinary collaborative in their development. Let's delve into how brain foundation models, or BFMs, are transforming the landscape of neuro AI and clinical neuroscience. These models represent a significant leap forward by harnessing advanced machine learning techniques to interpret complex brain signals at a scale. This slide is for conclusion, and at the end, we can conclude that at the core, BFMs merge transformer architectures with self-supervised learning applied to massive neural datasets. This combination enables the creation of highly scalable and general-purpose representations of brain activity. Think of it as building a versatile language for brain's signal, one that can be adapted across various neuroscience applications, pushing computational neuroscience into uncharted territory. One of the most exciting outcomes is the ability of these models to support cutting-edge clinical tools. For instance, BFMs have been instrumental in enhancing seizure detection systems, enabling more timely interventions. Additionally, they power brain-computer interfaces, which open new avenues for patient communication and control, especially for those with severe neurological impairments. These applications are not theoretical, they are already improving healthcare outcomes in real world settings. Beyond immediate clinical applications, BFMs also unlock prognostic capabilities. Take SleepFM as an example. It uses brain signals modeling to predict disease progression, offering the promise of earlier diagnosis and more personalized treatment strategies. This forward-looking insight can transform how we approach uh, the field and other brain-related conditions. However, the journey is not without challenges. Key hurdles remain, such as harmonizing diverse datasets across research centers, optimizing computational resources to handle enormous data volumes, mitigating biases that can arise from population differences, enhancing the interpretability of complex models, and ultimately earning the trust of clinicians who rely on these tools for critical decisions. Addressing these challenges requires more than technology. It calls for ethical and interdisciplinary collaboration. Uh, Success hinges on transparency, fairness, and aligning neuro AI development with ethical standards. Bringing together experts from neuroscience, artificial intelligence, and ethics fosters models that are not only powerful but also responsible and trustworthy. Ultimately, the ambition is to build brain models that clinicians and patients can confidently rely on, not just because they are accurate, but because they operate with integrity and respect for human values. This commitment to trustworthy brain modeling lays the foundation for sustainable, impactful advances in neurotechnology. As we move forward, we will explore how these foundational concepts translate into practical frameworks and methodologies, setting the stage for implementing BFMs across diverse neuro AI applications. My presentation is over. Thank you so much for paying attention, and I think it's time for goodbye. Bye.